Good morning, class. I welcome you to this first lecture. Since we just resumed from COVID-19 pandemic, and also due to ASU strike. Please, I want you to kindly test on the chat if you are hearing me and if you are seeing my screen. And also, we may try other
Other platform.
yes, we may try by like Google Meet. So I think
Yes.
for Google Meet there is no limitation as regards to that. Yes, Hassan Alinsi, I think you are raising your hands. Hassan Alinsi,
Good morning, sir.
good morning. How are you?
Fine, thank you, sir. The recorded class, sir, can it be posted on YouTube?
Yes, I will try as much as possible to put it on YouTube, and then you can. I will just put the link on LMS, so from there,
All right,
perhaps
sir.
you can get it.
All right,
Oh,
sir.
all
Thank
right,
you very
sir.
much, sir.
That's good,
So
sir. Thank you, sir.
is that okay?
Yes, sir, it is, sir.
Yes.
Yes.
I hope presently I'm having 99 students. Maybe there is someone who is yet to enter. Perhaps is the network from his or her own side.
All right,
But
sir.
anyway, once the record is going to be it's being recorded, and we hope subsequently we should be able to use other platform, and or I will get access to the Zoom class. I mean the Zoom that the university has, so that we'll be able to accommodate more students. Please kindly bear with me. I don't want to postpone this class. That is why we decided to continue. Uh,
Yes, sir.
Once this class starts now, I'm going to mute every one of you because I will be.
All right.
Yes, and also there is one student putting ZST. Is that the name? Is that the name of the student? Please, every student should use his or her own name. If the student refuse to, I will remove him from the class. Everybody should use his or her own name. Then let me confirm. Are you seeing my screen?
Yes, sir. We
Yes,
can see
sir.
your screen.
So I can start this class now. And then because this
Yes.
is this class, this Zoom I'm using is a basic Zoom. You can only have 40 minutes of lecture at a stretch. Are you with me?
Yes, sir.
So
Sir,
when
we
it is
can't
40
really hear you. It's
minutes, it
breaking.
is most likely.
Sir, there's
Are
a
you hearing
breaking.
me?
Somebody should turn up the mic. Someone to turn up. Your mic is disturbing the class.
Let me mute all. Let me mute every one of you first. Yes, are you hearing? Okay. So then once it is 40 minutes, I will class likely end. Then thereafter, so
Ẹ̀sán Dámilọ́lá, mute your mic.
so thereafter, you can use the same link again. to join the class back. So is that okay? Okay. So I will start the class immediately now. Dear student, you are welcome to this class, at least first class after the long holiday that was occasioned as a result of either ASU strike and then the pandemic. You will recall that this class, this particular course is in two parts. We have the design for timber elements, that is structures that are made of timber, either being used as columns or as beams, or could also be used as floor. Yes, as floor, especially in a story building. We have introduced this part of the course to you. We have extensively looked at the topic. In fact, we have completed the timber element design of the part of the course. I've already given you all the notes and the reading materials that you're supposed to have that will serve as guide for you in the timber element design. And I have also put the links for this material on LMS for you to download free of charge, so that you'll be able to have access to material. However, don't limit yourself to only this textbook. If you have any other textbook that is on timber element design based on BS 5628, then go ahead with it. It will also enrich you a lot. Yes, it is almost a year that have taken that we have done this timber element design. We hope that we have opportunity to do revision. We have opportunity to do revision, so that at least you will be able to get at least reminded of what we have done before. The second aspect of this course is concrete element design, which we have not started before the lockdown or the break. We all know what concrete is. So in this course, we are going to look at the design concept that we have for concrete design. We shall also consider analysis of section for specific concrete elements. For this particular course, because it is an introduction to reinforced concrete design, for the civil engineering students, you are still going to do many of reinforced concrete designs of different structures and elements. But for this particular, I'm not really, I think also building students too will also have opportunity. I don't know whether they still have another course that is based on concrete design. Be that as it may, for this particular class, you will be introduced to design of beams and slabs, design of columns, and design of pad foundation, basic part of this structural element. And if you look at any buildings are, especially a story buildings, are made up of all these structural elements. The only one that is not included here is the design of concrete wall, which is not part of this course. So Yes, concrete as construction material. Yes, you will have been saying what concrete is. Concrete is a composite material. It is composed of aggregates. So aggregates are sand and granite. And then you also have binder. That is cement that we normally have, be it Dangote cement or Lafarge cement or Pure Chem. The essence of this artificial elements, I mean composite and material, which is cement, or could also be supplementary cementitious material, SCM. They are most often than not being added to cement, either to reduce the clinker content, but in any way, it doesn't affect the properties of concrete. So then another constituent of concrete is water. If you add cement to sand and granite, there is no magic that can happen. They will never get binded. But adding water to it will make a reaction to occur between cement and water, and that is what we call hydration reaction. And this hydration reaction will produce a product that we call calcium silicate. The calcium silicate is the concrete that you see, the artificial stone that we use to build nearly all the structures that we found in our environment today. Most often than not, because we may wish to modify the properties of concrete, there are some chemicals that are being added. There are some chemicals that are being added. There are some chemicals that are being added to concrete to modify it, either to make it flowable, more flowable, or to improve the strength or any other properties that you may wish to modify. I want to mention that apart from water, there is no other material that is so consumed in large quantity other than concrete, because everything is being built today with concrete. Yes, I just want to, I want to confirm whether you are hearing me.
Yes, you can hear you.
Yes, sir. We can hear you, sir.
Okay. That's
Yes,
okay.
sir.
Yes, sir. Yes, sir.
Okay, thank you. I appreciate your cooperation that you are not disturbing the class. Yes, we have different types of concrete. We have mass concrete. In the mass concrete, it is only concrete that we produce, and it's only concrete that you lay. In this concrete, there are no other materials that is added apart from concrete, especially in a floor. When you have a floor, when you floor maybe the mass concrete over a wide area, they just put concrete and then they spread it. Then we have another type of concrete that we call reinforced concrete. This one you will have been seeing concrete that contains ions, that contains steel within it. We call them reinforcing bars. Reinforcing bar. So when you put steel within a concrete, that type of concrete is no more mass concrete, but a reinforced concrete. A reinforced concrete. Yes, Mr. Mustafa Raji, what do you want to say?
Okay, so I want to suggest that you disable waiting room because there are 89 participants now, and
I
people
should
are
what?
in the wait. Disable waiting room.
I should disable.
Waiting room.
Yes, the problem is that we have a limited number that this one that I'm using will take, and that
Yes,
is 100.
yes, 100. But there are 88 participants in the call now.
No, they were 100 already. Now you can see there are 99. Some left. Maybe they will still join. There is no way I can. I've allowed everybody. I've allowed
Okay.
everybody. I've admitted everybody. So we have 100
Okay.
already. So please, I've already mentioned this. It's a limitation which which we will try as much as possible to avoid in subsequent class. Is that okay?
All right, sir. All right, sir.
Okay. Thank you. So then, the other type of concrete is what we call composite concrete. Composite concrete, this type of concrete, it's more or less like a reinforced concrete, but it contains more other, that is when you are combining steel. I mean the steel section. When you are combining the steel section with concrete or timber with concrete, then we have what we call composite concrete. For a precast concrete, precast concrete, most often than not, they are type of concrete elements that are fabricated at industry, at the factory, and then they are taken to the site for assemblage. Because that is, it was cast before being used. Unlike an in situ concrete, where the concrete is cast on the site where it is going to be used. Another type of concrete is self-compacting concrete. Self-compacting concrete. That is the type of concrete that you don't need vibrator. You just lay it and then it will fill all the formwork without vibrating it. So with a self-compacting concrete, you save cost of vibration. Then the last but not the least, we have what we call pre-stressed concrete. Pre-stressed concrete. This is the type of concrete that is more or less like a reinforced, but instead of using steel for reinforcing, wires and tendons are used in for the pre-stressed concrete. I am sure, I'm sure, and I'm aware that for civil engineering students at part 5, then you will do design of pre-stressed concrete. But for this class, we are going to do the reinforced concrete. That is concrete that contains steel. Now, somebody is marking. So, yes, Mr. Mustafa Raji, what is the problem again?
Sir, for that composite concrete, I did not get the explanation.
I'm saying composite concrete, you have a steel section. We have a steel section that are being used along with concrete. But that is not a problem for you. At times, if you have timber, we have timber that has been used along with a concrete, is a composite. You have a concrete that is being used with steel section. It's different from, this is like, if you look at where my cursor is now, you can see some steel ions there. These are called the steel reinforcing bar. It's different from steel section. In a steel section, especially if you see anywhere else where what they normally use for the column and what they normally use for the roof, they are called steel sections. So if you use concrete along with steel section, then you say it's a composite concrete. Is that okay? So this class,
Yes,
as I mentioned, so yes, we there is a notice already that we have spent the 40 minutes. We are very close to 40 minutes. Once, are you hearing me?
Yes, sir.
Yes, sir.
Yes,
Sir.
one,
Yes, sir. We can hear
Yes,
you,
sir.
sir.
yes, once this class close, we can rejoin again for another 40 minutes using the same link. It's just like I did mention, we will try as much as possible not to use the one that was is being used by the university. Then we'll be able to save all these problems. So quickly, the first concrete is made up of two different materials that are being brought together. That is concrete and steel. The steel is used for the reinforcement to add more quality to concrete. Then concrete, why do we need to reinforce concrete with steel? It is because of the properties of concrete. Concrete is weak in tension. That is why when you subject concrete into a flexural state, you will see at the bottom of this concrete, you will see that there are cracks there. And if there is no reinforcement within it, then there is possibility for this concrete to break into two. And since steel is good at resisting tensile stress, that is why we incorporated steel into concrete to, to add to the ability of the reinforced concrete in resisting in resisting tension. And if you look at this table, we have some properties here. We have the concrete, we have steel. For tension, concrete is poor. For steel, steel is good. For compression, concrete is good, steel is also good. That is why you will see in some section, in some buildings, they use steel section as columns, as compression member. Then for shear, concrete can always shear, that is ability to split into two. But for steel, that is not always possible. So we have for durability, concrete is a very durable material. It doesn't corrode. It doesn't water doesn't affect it so much. Unlike steel, steel can corrode in the presence of air, that is oxygen. So then, what exactly are we really designing in reinforced concrete? There are some basic things we must have in mind when we are saying we are designing reinforced concrete elements. Our interest is determining size of concrete element. If you want to decide, for instance, now you want to design a beam. Beam always have beams always have size, either rectangular, either square. You have to determine the size. Then you also determine the size of steel to use. Steels are produced from the factory at different sizes, in different sizes. We have some that are 6 millimeter in size, 8 millimeter, 10 millimeter, 12 millimeter, 16 millimeter, 20 millimeter, then 24 millimeter, and 36. These are standard sizes of reinforcing steel or rebar, reinforcing bar that you find in market. Then we also want to determine location of the steel. Where exactly do we put the steel within the concrete matrix? Do we put it at the bottom? Do we put it at the top? Do we put it on the sides? And finally, how do we arrange this reinforcement within the concrete? All of this are what we need to know under when you are doing reinforced concrete design. If you look at this figure, you will see that when the concrete element is loaded, it buckles, and then we have compression zone. It's divided into two zones. We have the compression zone. In this section, the concrete doesn't fail because concrete is good in this section.
But at the bottom, because there is tension at the bottom, you can see the concrete is already cracked. And if not because of this reinforcement, this steel that we put there, this concrete will continue, the crack will progress to the other end, and it will make the concrete to break into two. When you did strength of materials in 200 level, you did a lot of stress diagram, stress and strain diagram. So in the compression zone, we have this is positive. In the tension zone, we have this is a negative. If you cut this beam into two, that is, you cut the cross section, you have something like this. And you have two reinforcing bar that is put at the bottom of the concrete element. So sorry. So in the design of reinforced concrete element, the concept the concept is you want a safe structure under the worst loading condition, and at the same time, once a concrete member is designed, we don't want it to deform in such a way that it will affect its appearance. So these are the two major objectives that the design of reinforced concrete element looks to achieve or seems to achieve. Once it is designed, it doesn't fail under worst loading condition. And at the same time, the appearance, for instance, now if you see a building that is deflecting, and it is having a lot of cracks on it, nobody, though it doesn't collapse, nobody will be willing and feeling comfortable to stay in such structure. So we don't want structure to deflect excessively. We don't want structure to fail by having a lot of cracks. Or that such structure must be able to withstand, so at least to a larger extent, the fire, maybe in case of fire, so that you have some what you call the fire resistance to damage. You have different types of design methods. You have different design methods that has been in history of reinforced concrete design. We have permissible stress method. You will remember that I made mention of these three methods during the timber class. For permissible stress method, in this method, the material strength is only factored, while the load are not factored. And the material strength is factored in such a way that the properties is divided by factor of safety. The code of practice that adopt this permissible stress method is CP112. Then we have another method we call load factor method. In the load factor method, as the name implies, once load is estimated that your structures intends to carry, let's say a structure wants to carry a load of 30 kilonewton, then you will factor it by multiplying that 30 kilonewton by a factor. Who is this person that is putting marks on our drawing? So then the code of practice that uses this method is CP114. That is for concrete. But because of the limitation of the permissible stress method, because it doesn't factor load, and because of the limitation of the load factor method, because it doesn't factor material strength, both load and material strength are very, very vital to stability of any reinforced concrete structure. So in order to eliminate the weaknesses of these two methods, new method was developed, and that method is what they call limit state method. In the limit state method, both material strength and working load are factored by factor of safety. And this method, the principle, guiding principle, the design guidelines are embedded, are put together under BS 8110. You have part one, we have part two, we have part three. Part one is for general design, which I've already asked you to get, and I hope many of you must already have the code with you. But for the part two is more of analytics, more of mathematical representation of determining cracks, which we seldom use. And then part three contains charts of for concrete for column design. You have a lot of charts for column design, and because we are also going to look at column design, at least the basic introduction to column design, you will also need BS 8110 part 3. Then in this code, BS 8110, I mean in this method, limit state method, you have design load. That is the load that you are going to use to design your structure can be obtained by multiplying your working load. The working load is the load that you have estimated, that okay, this structure is going to contain so number of people, and it's going to put, you are going to put some furnitures in it, and then all together is going to have all this amount of load. That load is what we call the working load, and then you multiply by factor of safety, just to jack it up a little bit, so that it will be able to take care of some unforeseen uh, increase in load. But for the design strength, the material strength, most often than not, the material strength that we have in the market may not be as high, or may not be as the same as the code envisage. So that is why you assume that the material strength you are going to use is a bit lower, so that you will be able, so that you'll be able to have at least some level of confidence that your material will not be stretched beyond its capacity. So you divide the material strength by factor of safety. Now, limit state design. Limit state design has aim. The aim of the limit state design, you will see most of this information, I mean, about the limit state design as introduction in BS 8110. I will encourage you to take your BS 8110 at your leisure time. Read the introduction to limit state design further, and also you will also get more information from the reference material I have already given you. The aim is to achieve acceptable probabilities that a restructure will not become unfit for its intended use. You want a structure to be used maybe as residential, or a dancing hall, or an auditorium. And it is expected that this structure will, will be in use for some years. So the essence of limit state design, the aim is that the structure must not fail before its lifetime, and the structure must not be unfit for use for its intended usage. For instance, now you cannot design a structure to be used as a hall, And at the time, we now say people should not use it as a all again because of the fear of failure. It means you have defeated the aim of the design initially. We have two major types of limit states. When you say limit, it means you have what you call a boundary above which nothing should be. So we have what we call the ultimate limit state. In the ultimate limit state, if the ultimate limit state is exceeded, the repercussion is that the concrete will fail, the concrete will collapse. And that will always happen when the structure is exposed far, far beyond the shearing force it can resist or the bending moment it can resist. If it is more than this, then there is possibility of such structure to collapse. Then it could also be as a result of buckling and overturning are also taken into consideration, because if you have a structure and then it overturns, then definitely that design is faulty somewhere. That is the first part of ultimate limit state. The second part of the limit state design is serviceability limit state. As the name implies, service. You expect the structure to render the service for which it is produced. So the structure must be able to withstand physical damage. The physical damage could be as a result of bending, cracks, excessive vibration, fatigue, fire resistance, and then durability. So you can now see that taking these two limit states into consideration, then you seems to have a very good and structure that will be able to serve the purpose. The procedure is we make provision for the structure to prevent ultimate limit state to reach, and then we check for serviceability limit state. So this is just the summary of what we are going to get when we start, what you are going to see when we start the design of reinforced concrete elements. We will first and foremost provide, make provisions for which that concrete element will not reach the limit state within the years, within the design, the lifespan of the structure. And then once that is there, then you also check whether the serviceability limit state will be exceeded or not. You will say a structure is well designed if both the ultimate limit state and serviceability limit state do not reach before the lifespan of the structure. Marty, are you hearing me?
Yes, sir.
Okay.
Yes.
Yes, sir.
Yes, sir.
Okay. So
Yes, sir.
material stress and design load. Because we are using material for our design, and then because your material which you want to use as for your structural element will be exposed to usage. You as human being, the student in a classroom, for instance now, you are a source of load to that structure. So there is need to estimate load, and at the same time, there is need to know the strength of your materials. We have what we call the characteristic strength. For the characteristic strength, especially for either reinforced for the concrete, because most often than not, steel are produced in industry. They have guidelines, they have specifications for which they produce these iron bars, I mean the steel bars. So as designer or as engineer, you don't have control over the steel design. You don't have control over what should be the reinforcing steel that you will use. It is what you will see in the market that you will design towards. But for concrete, you are the one that will produce the concrete. Or even if you are not the one that will produce the concrete, you will buy the concrete. But you have to specify, so you have to specify the characteristics. You have to specify the strength of the concrete that you want. Maybe if you want to buy. But what do you mean by characteristic strength of concrete? Of concrete. In order to determine the compressive strength of concrete, we carry out compression tests. We carry out compression. We can't hear you.
He muted it.
Hello, sir. We can't hear you, sir. Sir, we can't hear you. Sir, we can't hear.
He muted himself. That means he's not
He
saying
muted
anything.
himself.
So sorry. Anyway, so you do several tests. You do several tests. Your compression test. You do several of it, and then you have list of figures in form of statistics. You determine the mean of the results, the compressive strength test result that you have. You determine the mean. You know how to determine the mean in statistics. Then you determine the standard deviation. So using this expression, Fk, that is the characteristic strength of concrete, is equal to the mean of the strength that you carried out minus 1.64 times standard deviation. This, whatever you get from this expression is what we call the characteristic strength of concrete. You are going to come across this term a lot in this course. You can see the normal graph for whatever result that you have obtained. So the characteristics, and this is the minimum strength above which you are not expected to exceed. So that is why you come on the other side. But for characteristics load, it has a range, either on the right of the mean or on the left of the mean. When you multiply by 1.64 with the standard deviation, as we have this. However, because you don't normally have values or data for loads like that. So in order to make design relatively easier, there is a code that has given different types of loading for buildings. We call it BS6399. We call them design loads for buildings. So this particular document contains different types of structures and the recommended loads that could be used as either imposed load. So this is how you determine the characteristic load and then the characteristic material strength. Then because you want to design, you need to determine your design. You need to find your design design strength. The design strength will be the characteristic strength of the concrete divided by factor of safety. The value of gamma m, which is the factor of safety for the material, are provided in BS 8110 part 1. You will get it, yes, in one of the tables there, which I will show to you in our subsequent class. For the design load, is the characteristics load multiplied by the factor of safety for the load, which I had mentioned before when I was talking about limit state design. Gamma F is the factor of safety, which is also provided in the code BS 8110 part 1. I guess this one should be in table 2.5 or thereabout. Now, why do we need to factor our load? Why do we need to factor the strength material? The essence of factoring is to take care of design assumption, because there are some things you will assume. So if your assumption is underestimation, the factor of safety will be able to take care of it. Inaccuracies in calculation, maybe doing while you are doing some calculation, though this should not be excessive. Errors in calculation or minor errors in calculation will be taken care of by partial factor of safety. The unforeseen stress distribution Because in the the stress distribution within the concrete in concrete is a very complex system. Most often than not, a simplified stress distribution is often used. And what then matter is that because you have made an assumption, you simplify the stress distribution, whatever small error that you have taken care of, that you didn't take care of, as a result of your assumption, will be taken care of by a factor of safety. Also, construction inaccuracies. These are the reasons why factor of safety are used. Now, we have different combination of loadings. We have different combination of loadings that you may have on a structure. You have different combinations. You can have a dead load and imposed load. Imposed load are any other load are loads that are not permanent. That are not permanent. The earth and water, that is when you have, for instance, you have a wall, maybe a retaining wall to retain some amount of
Can't hear you, sir.
He is mute.
somebody
Yeah.
put that
Okay.
now. So you will find this table, a BSA 210 table 2.1. For the ultimate limit states, these are factors for dead load, that is loads that are permanent in your structure, that are expected to be permanent, is taken to be 1.4. Loads that are not permanent, like furniture, like human being, and any other thing that are expected to be moved, they are called imposed load. Some textbooks you will find them as life load. They call them life load. Either life load or dead load, they mean the same. So in that case, for imposed load, you have 1.6. If we have earth and water in it, then you will factor by 1. In that case, if you earth and water, if they are earth and water, the dead load is, you will use 1.0. But if there are other materials, it will be 1.4. You don't use imposed load when we have earth and water, that is earth and water that serve as load. You use them as if because you can always determine that one. Then for ultimate limit state, if you have earth and water, then you have 1.4. If you have wind load, normally the wind load is not taken into consideration here. For serviceability limit state, all the whether dead load, imposed load, or wind load, they are taken to be 1. The factor of safety is taken to be 1. Yes, Udaifa Kosim, any problem?
So I want to ask a question. My question is that which load is the one for art?
The one for earth and water, when you earth is just like soil. When we have water
Okay, sir.
in the soil, it will be an imposed, and then you will factor it by 1.4. Is that okay?
Yes, sir.
Okay.
Thanks, sir.
Then if you're having dead load and wind alone, because you have different types of loading, it can be dead, it can be imposed, it can be wind. If you have a combination of dead and imposed, you use this factor 1.6, 1.4 for dead, 1.6 for imposed under ultimate limit state. But under serviceability limit state, you use 1 for both dead and imposed. But for a combination of dead and wind load, for instance, maybe in a high-rise building where the effect of load is likely to be noticed. Who is Bello Alima? Why are you marking this? I think I will need to mute this my annotation. Okay. Okay, yes, I've disabled them. Now, here, if you have the three combined together, dead and imposed and wind, instead of using 1.4 when we have dead and imposed, you will use 1.2. For the imposed, you will use 1.2. For the earth, if there is earth and water, you use 1.2. For the wind, you use 1.2. But for serviceability limit state, the load that you have is still the same. You only factor it by 1. Now let us to demonstrate this. In order to determine design load, this example 1 says determine the design load for structure that has dead load of 45 kilonewton and imposed load of 12 kilonewton. You will see that we will consider the load combination number 1 because it is dead and imposed. So design load will be dead load multiplied by factor of safety plus imposed load multiplied by factor of safety. That will be the total design load which your structure is expected to be designed for. This 45 kilonewton is your working load which you have estimated, and this is also a working load which you have estimated. Because there may be some mistakes while estimating this load. Those mistakes are being taken care of by this factor of safety. So at the end of the day, you have a design load of 82.2 kilonewton. So this is how the load of a structure, design load of a structure is estimated. Yes, I have another example here. We want to see how we can use the two, all these, the three methods. This question says determine the cross-sectional area of a mild steel that supports a total dead load of 5 kilonewton and an imposed load of 3 kilonewton. The characteristic yield stress of the mild steel. This is the mild steel that you buy in the market. Though in Nigerian market, you can't find 250 Newton per millimeter squared anymore. The strength of material you find in the market, in Nigerian market this day, is 460. Or 460, it may be lower. So we want to carry out the calculation using the load factor method. You want to use the load factor method of design, and then we use a load factor of 1.6, for instance. A permissible stress design with a load factor of 1.6, with a factor of 1.6. In the permissible stress design, how do we determine the strength of the stress of the material then? You will define the characteristic yield stress by the factor of safety. So for the design load now, our total load is 5 plus 3. That is the total load from 5 plus 3. And then because we are on the load factor method, then we have been given the factor to use, which is 1.6. When you multiply this by this, it will give you 12.8 kilonewton. To now determine the area of steel required, this is the load. You know, stress is equal to area, is equal to force over area. And if you want to determine the area, it will be stress, it will be force all over stress. So when you divide this by this, you will get 51.2 millimeters. So this is the amount of the area of steel that you require to incorporate into that concrete. And if you know the diameter of steel to use, you can determine the area of 1 bar, and then from here you'll be able to determine the number of reinforcing steel you will require. But for permissible stress method, you don't factor load, so the load is still 8 kilonewton. But you factor material stress by dividing 250 divided by 1.6. That will give you 156.25 Newton per millimeter squared. So once you have this stress, then you can determine your load. You can determine your load, sorry. So you can determine this. This is your load is 5 kilonewton. If you take it to Newton, that is 5,000 divided by the stress. You have the area to be 32 millimeter squared. Then for design for limit state method, in the limit state method, you will factor the imposed load, you will factor the you factor dead load and you factor imposed load. The total load will now be 11.8 kilonewton. You also factor the material stress. The material stress is given to be 1.05. You get the material stress here. So from here, you determine the area of steel required. So if you look at this very well, you will see that in the load factor, you will use more reinforcement than in a permissible stress method. Why a design load as a combination comes between the load factor and then permissible stress method. Now, so perhaps I wouldn't know, we have about 15, anyway, because we are recording, they always get this information. Now, let me check if you have. Please, how do you get 5,000? The load is 5 kilonewton. When you take it to Newton, you multiply by 1,000, making it 5,000. The same thing, that 12.8 kilonewton that we had the other time, if you multiply it by 5,000, by 1,000, and then you divide by that stress, you will get that value. Then, analysis of section. Before you can say you want to design, you must have done analysis. I know you have done some analysis when you are doing strength of materials at 200 level, when you plotted the shear strength, shear force diagram, bending moment diagram. All what you did then, you are analyzing a beam or you are analyzing a column, whatever. But in this case now, we want to analyze a section, not the elevation, but the section. When you cut a section of a beam, you will see something like a rectangle, not the length. So each structural element is analyzed and designed. We have the slab, beam, column, wall. Then analysis is required to determine what we need to, the purpose of analyzing is to determine the moment and then to determine the shearing force. And the fundamental principles is that the stresses and strains are related by the material properties. So I know you must have come across this. This is when you load concrete, this is how it looks like. This is how it's the way it is stressed until it finally breaks. And then we have, this is a stress strain diagram, At this particular point, the material is still obeying Hooke's law until it becomes parabolic, because it is not purely, concrete is not purely elastic material. So that is why it doesn't fail at a particular point. So here you have the strain for this place. This is the FCU, that is the characteristic strength of the steel, of the concrete, divided by the load factor. Then at the point where we have the, what we call the stress, the highest stress here is determined from 0.67 FCU. You will find this table, you will find this figure also in your code. You also find this figure also in your code. But the strain at which the concrete could extend before it breaks, before it finally fails, is what we consider 0.0035. The same thing also goes for steel. When steel is loaded, you have something like this. Because steel is more or less, steel obeys more of Hooke's law than concrete. That is why you will see how it goes. This is how you can see a very straight stress strain diagram for concrete. So we'll get some information from here. This is this is where the design stress is. That is why we have the characteristics, the characteristic strength of the steel divided by load factor. There, this is the characteristic strength of the concrete. It's modified by 0.67 because it is not purely rectangle. It is not purely rectangle, it is parabolic. But because we need to simplify, that is why it is being converted to rectangular shape, and then it is being factored by 0.67. We are going to talk more about this when we get into design. If you look at your figure, if you look at your table, your code BS8110, you will find this figure, this first figure in figure 2.1, while you'll find this one in figure 2.2. So may I stop a bit here and then maybe get one or two responses from you? If you have anything, kindly. What about 3 kilonewton? 3 kilonewton is the imposed load. Is the 3 kilonewton is imposed load?
Sir, will you be dropping this typo, sir?
Yes, okay. Yes, sorry, here. You're supposed to use 8 kilonewton. Are you with me?
Yes.
You're supposed to use 8 kilonewton. That will give you 8,000. Then definitely this will not be 32 millimeters squared again. That's okay. So
Yes,
this
sir.
will be corrected in the. I'm still going to send the PowerPoint presentation. I'll put it on the LMS for you to go through it. So we'll correct this one. Is that okay?
Yes, sir.
So now, so it shows that you are following up. That's good. Now, this is a bit of a stress diagram. We have spent, this class supposed to end by 9. Okay, this we have spent already 1 hour. So anyway,
You are muted, sir. Yeah, he knows, I think.
so we have this is a cross section of a typical beam in form of a rectangle. We have the depth of the beam. We have the breadth of the beam when you cut a section. This cross section is having steel members at the bottom, is also having steel at the top. There is a point, there is a line, an imaginary line. Within that, we call it neutral axis. This is the neutral axis. That is where the compression zone is transiting into tension zone. The reinforcement we are putting here is resisting compression along with concrete, while the reinforcement we are putting at the bottom here is resisting tension. You can see the notation for compression steel, A prime S, and then for tension steel is not having